Hi everyone. Today we are going to move on to section 8.7. This is going to be the final section in chapter 8 that we will be looking at. And in this section we're going to discuss and review what an acid-base titration is. So if you recall from grade 11, we had performed a variety of titrations. And so this is a process where we add a known solute, which we call the titrant, into a solution of unknown concentration, which we call the sample. And so the purpose of a titration is to determine the amount. Okay, so when we refer to the amount, we are referring to the number of moles. Okay, we're referring to the amount refers to the number of moles within the sample. So generally speaking, when we try to determine the concentration, okay, the unknown concentration, which is in moles per liter of the sample, it is going to be collected in a flask. All right, so this is generally what a titration would look like. So we would place the known concentration, which is my titrant, into the burette. All right, this is called the burette. It's calibrated to 2 decimal places. It's called our burette. And in this case, we're placing a known concentration of 0.1 moles per liter of sodium hydroxide, which is a base. And we're dispensing little by little into a known sample volume of my unknown, all right, which is my sample, and we place that into an Erlenmeyer flask. Okay, an Erlenmeyer flask is normally what we use in order to collect and neutralize the acid. All right, so normally we would put the acid inside the flask, and the titrant, which is my base, would be in the burette. I add drop by drop into the flask until we see a color change take place. So as we're going through the process, what you'll start to notice as the drops are being added to the flask, you start to see color changes taking place. It goes in and out of color as we rotate and spin the flask to ensure that all of the sodium hydroxide is mixing completely with the nitric acid, which is my unknown sample that we're looking for. And eventually we're going to reach what we call our endpoint. This is where the indicator that we added to the flask changes color, all right, and that color persists. So we've got 2 important definitions that we need to make sure we know the difference between, and that is the equivalence point and the end point. So our equivalence point in a titration is going to measure the quantitative, which is numerically the amount of moles needed of the titrant, which is the known concentration, where it chemically is equivalent to the unknown sample. All right, so this is a neutralization reaction, and so therefore the amount of acid is going to equal the amount of moles, or the amount of moles of acid will equal the amount of moles of base. At this point, we've reached the equivalence point. The end point is where we see a very sharp change in a measurable characteristic property, all right, such as a color change using an acid-base indicator. So ideally, you want to find an indicator, an acid-base indicator, which is as close as possible to that equivalence point, all right, is what you want to do. So when we titrate a strong acid to a strong base, this will tell us that the number of moles of acid is equal to the moles of base. All right, so we can therefore have this formula that we can use, where CAVA is equal to CBVB. So remembering that concentration is equal to the moles divided by the volume. All right, so we may be using this formula when it is a 1-to-1 mole ratio. Now, if we were to plot the pH of a strong acid-base titration, it is always going to have a very characteristic curve um, that will be distinguished for a pH or an acid-base titration. The curves are all going to look very, very similar. So on the onset, it's very, very inside the flask. We'll see that it has a very strong acid or hydrogen ion concentration. But as we begin to add the NaOH, it starts to become less acidic. Okay, and then at one point, which is the equivalence point, at this point we're going to have the equal number of moles. But after that point, what's going to happen is you're going to have an excess of hydroxide ions if you continue to add more NaOH, okay, until it becomes much higher. So the midpoint of this curve here, from here to here, the midpoint here is going to be the equivalence point, all right? And at that point, we have exactly equal numbers of hydroxide ions equals the number of hydrogen ions, okay? This is a very characteristic curve for pH of an acid-base titration. And so we see how it's gradually, the pH is going up as we add base. And then once it achieves that equivalence point, we then exceed the concentration of hydroxide. It becomes greater than the hydrogen ions, all right, if we were to continue adding more of the base. All right, so that is a characteristic curve that helps you in determining the actual equivalence point. So just a quick recall of some other very important terminology, a lot of new terminology when we're talking about a titration, and that's the sample. This is what we're trying to determine the concentration, how many moles there are within the given sample. The burette is the calibrated tube that delivers the known concentration into the flask. Our standard solution is used to, which is our known concentration, and helps us determine the concentration of the unknown sample. And then indicators help us to determine the equivalence point. Okay, it marks the endpoint. All right, so ideally we do wish to have a indicator that has an endpoint very close to the equivalence point. All right, and that'll help us determine the concentration. Now, next important thing, which we did do in grade 11, you should have all performed a titration in grade 11, is we're going to do a quick review of the calculations that are involved when we perform a titration. So this is some typical data that you would receive during a titration. So normally when we do a titration, you would like to do several trials, all right, to try to get as close a volume as possible. We want to try to be as precise as possible. So in each of the trials, in the flask, we place exactly 10 milliliters of the unknown sulfuric acid. Okay, and so we're going to be titrating against a known concentration of 0.1 moles of NaOH, okay, which is my base. So we perform the experiment. So in the burette, we would fill up the burette to about 50 milliliters. And so we would take this initial reading of 0.1. And when we do the titration, once we see our color change go from pink to, goes from colorless to pink, we get a final value of 12.52 milliliters. So by subtracting these two numbers, final minus initial, we see that we required 12.42 milliliters of the known sodium hydroxide solution, okay, to neutralize our 10 milliliters of sulfuric acid. Now this value here now becomes the initial for the second trial. All right, so now we take a new flask with 10 milliliters of our sample, and we do perform a second titration, and it reaches 24.98. By subtracting these two, we get a value of 12.46. All right, which is pretty close to the 12.42. So we see that we've got some pretty consistent results here. And then we do a final trial. Usually we do them in threes. So this is our starting point for our third trial. And it goes to 31.62 with a new sample of 10 milliliters. And so this value here equals 12.64. So they're all very, very close. And so now the first step is to find the average volume of these titrants that were used. So this is pretty easy in order to do. And so what we do here is we're going to find the volume of the base, and it's just taking these three values, 12.42 milliliters plus 12.46 milliliters, and we're going to take our last trial value, which is 12.64 milliliters. We're going to take those numbers and we're going to divide it by 3. That is going to give us the volume of base used, which is 12.47 milliliters. Okay, so that is our volume there. Okay, well, you know what? Let's keep a couple extra. If we were to look this up, we would see that keeping one extra decimal place, and we'll round off in the end. So it's 12.467 milliliters. So now, what I didn't include here is some of the given information. We know that the volume of the acid that we used in each of the flasks was 10 milliliters, keeping 2 decimal places. The concentration is what we're looking for. All right. We've got the volume of my base. All right, we just calculated it here, and we're going to place that in this number right here, and so that is actually 12.467 milliliters. And we were also given the known concentration. In the question, we were told that in the burette we've got 0.0 moles per liter. All right, so that's the given information here. So the first thing we need to do is, since we want to find concentration, our volumes need to be in liters. So I'm going to do that right away at the very beginning. So if I'm going to do the volume of my base, which is the 12.467 milliliters, I'm going to divide it by 1,000. And that's going to give me 0.01247 liters. And my volume of my acid is going to be my 10 mils, which I'm going to divide by 1,000, because in 1 liter I have 1,000 milliliters. And that is going to equal 0.100. Sorry, I didn't do that one. It's 0.1, and it's 100 liters. All right, so we've got those converted to liters. And now to do this, we always need to start off with our balanced chemical equation for this neutralization reaction. So we see that we've got sodium hydroxide reacting with sulfuric acid, and this is going to produce H2O and my salt, which is Na2SO4. All right, so you always need to start off with the balanced equation. So now I need to balance it. I'm going to place a 2 here, and I'm going to put a 2 here, and so now I am balanced. And so what you'll notice here, folks, is that we got a ratio of 1 to 2 of acid. This is my base to my acid. Okay, so at this point we need to solve using our mole ratio. Since this ratio here is not 1 to 1, you cannot use the formula CAVA is equal to CBVB. All right, we cannot use that formula, so we're going to have to do we will have to, I'll write that down so that you remember that. Okay, so since the mole ratio is not 1 to 1 here, okay, so this is what you got to determine here. It's not 1 to 1. We cannot use CAVA equals CBVB. You can only use that formula if it is a 1 to 1 mole ratio. We must use stoichiometry. All right, so we're going to work through that on our next page, okay, in order to solve. All right, so that's step 4. Okay, so we want to find the amount of the substance. So don't forget, when we're referring to amount, we're referring to the moles. All right, that's what we're looking for. So you want to know the number of moles of the known concentration. So in this case, the moles of the base is equal to the number, concentration is equal to the moles of the base over my volume. Okay, so if we're going to find our moles, rearranging our equation, so it equals CBVB. And so I'm going to plug that in. I know the concentration is 1.1 moles per liter. And I've got decimal 0.1247 liters. And when I work that all out, I get 1.247, keeping an extra decimal place there, times 10 to the negative 3 moles. Okay, so now I've got my number of moles of my known base. Now we're going to use our mole ratio from the balanced chemical equation to determine the moles of the unknown. All right, so that's what we're going to do here. So to find the moles of my acid, it's equal to this moles that we just found, which is 1.4247 times 10 to the negative 3 moles of NaOH. And then we're going to times it by our converting factor from the balanced equation. I got 1 mole of H2SO4 over 2 moles of NaOH. And these numbers here, folks, we get from our balanced, these are from the coefficients from our balanced equation. Okay, coefficients from the balanced equation, just so that you remember. Okay, that's from the balanced equation. And so when I work this out, we see here, look at my moles of NaOH cancels with moles of NaOH. So I'm going to take this 1.247 times 10 to the negative, divide it by 2, and it's going to give me an answer of 6.233 times 10 to the negative 4 moles of H2SO4. So now I know my moles of H2SO4. Now that I got my moles, I can now calculate the concentration of my acid, because the concentration of the acid is equal to the moles of the acid, which we just calculated in step 5, divided by the volume, which is 10 milliliters. Okay, so I'm going to plug that into my equation, and I'm going to divide by my volume in liters. So that's why we did that way back in step number 2. And when I work that out, I get 6.233 times 10 to the negative 2 moles per liter. All right, so this represents my concentration. So based on this question, so to write this to the proper significant digits, it would be to 3 significant digits. So the correct answer here is 6.23. All right, that's 3 significant digits. This would represent the concentration of my acid, okay, of H2SO4. All right, that's the concentration that we're looking for. All right, to the correct significant digits. All right, so now we're going to try one more example. Okay, in this example, pretty similar to the one we just did. Always write down the information that we're given. Okay, so we see here I got volume of my acid is 15.52 milliliters. I would recommend that you change that, convert it right away to liters so that you have it ready for your calculations. We know the concentration of the acid, it's 0.1. Okay, that's all given to us in that first part of the sentence. And it says that we're titrating 25 milliliters, so this represents my volume of my base, which is 25 milliliters. And once again, I would convert that right away to liters by dividing by 1,000. And we're looking for the concentration of my base. That's what I'm looking for. So we need to start with a balanced equation. So I've got HCl reacting with barium hydroxide. So don't forget, we always need to make sure we've got the correct chemical formulas. This is a neutralization reaction, so it forms water, liquid water, H2O, plus my salt, which is barium chloride. Okay, so this is a special type of double displacement reaction. Once again, I got to balance it. And we see here that once again, we got a 2-to-1 ratio. So we need to follow all of those same steps. So first is find, this is my known. We see here, because we have both the volume and the concentration, this is my unknown. This is the one that I'm looking for. Okay, so therefore, we are going to find the moles of my acid. Okay, so it's rearranging the equation, and that's plug in our numbers here. From the given, making sure that my volume here is in liters in order for us to multiply, and this now gives me my volume of my number of moles of 1.552, keeping an extra decimal place there, times 10 to the negative 3 moles. Next step is find the mole ratio using stoichiometry. To get my moles of my base. So I just calculated 1.552 times 10 to the negative 3 moles of HCl. And the mole ratio from the balanced equation is 1 mole of barium hydroxide over 2 moles of HCl. And we're going to divide. So notice my moles of HCl cancel with moles of HCl. So we're going to divide this to get our moles of base. And that is going to equal 7.8 times 10 to the negative 4 moles of barium hydroxide, okay, which is my base. And now my last step, step number 3, we are going to find the concentration of my base. So the concentration of the base, plugging in my numbers here, I got my 7.8 times 10 to the negative 4 moles over the volume in liters. And then this is going to give us our concentration. So it's 3.12 going to 3 significant digits times 10 to the negative 2 moles per liter. All right, so this represents the concentration of the base. All right, this is what we're looking for. So that is my final answer. Okay. All right, so folks, ideally I would like you to try these homework questions here from the textbooks to review. It is important. You will be doing some titrations next year in post-secondary, so please make sure you know how to practice and do these questions that are listed. All right, good luck, and we'll see you in the next lesson.